Today we are walking through the paper titled Hyperloop Transformers.
What is the main problem this paper is trying to solve?
The paper is about making language models more parameter efficient. Standard architecture work often asks how to get better quality under a compute or latency budget. But edge and on-device settings also care about the memory footprint. The authors want a transformer that keeps quality high while carrying far fewer parameters.
So the baseline pressure is memory.
A loop transformer reuses the same transformer layers across depth. Instead of paying for a fresh set of weights at every effective layer, the model runs a block repeatedly. That saves parameters. But the paper reports that vanilla loop transformers can fall behind depth-match transformer baselines on perplexity.
Where do hyperconnections enter the story?
Hyperconnections expand the residual stream into several parallel streams. Then use learned mixing to decide how information flows into and out of a transformer sublayer. The useful part here is that the expensive attention and MLP computations still operate on the usual channel size, while the residual pathway can carry richer state.
If hyperconnections add richer residual streams, why not put them everywhere?
That is the key design choice. Hyperloop transformers apply hyperconnections only after each loop of the middle block. This means the model gets the benefit of parallel residual streams at loop boundaries, while adding only about 150 to 300,000 parameters over the vanilla looped model in the main comparisons. Now let us look at the architecture diagram.
On this diagram, what changes from the vanilla looped version to Hyperloop?
The vanilla looped model sends one residual stream around the repeated middle block. Hyperloop keeps the begin and end blocks, still loops the middle block, but writes into several parallel residual streams after each pass through the loop. That gives later loop passes a richer memory of what previous passes produced.
Does the loop block know which pass through the loop it is on?
Yes. After the middle block, the model adds a loop position embedding. The paper then repeats this process for several loops and finally averages the parallel streams before feeding the result into the end block. So the loop is weight reuse, but it is not blind repetition. One useful equation is the ordinary transformer update, because it gives us the baseline that the looped block is reusing.
What should I pick from that equation without getting lost in the symbols?
It defines one layer update. The representation math effect cell goes through attention, then the attention output is added back through a residual connection. The MLP then updates that hidden state and adds another residual connection. Hyperloop keeps this transformer machinery, but reuses the middle block weights across repeated passes. The paper also writes the hyperconnected update explicitly. This equation is about how the matrix-valued residual stream is mixed before and after the sublayer.
What are those 3H terms doing?
MathBFHDEX premixes the parallel residual streams before the transformer sublayer sees them. MathBFHDEX post controls how the sublayer output is written back. MathBFHDEX trays mixes the residual streams themselves. The paper introduces this form to let a looped model carry more state without making attention and MLP much more expensive.
What evidence do they use to show that the architecture is better?
The main evidence is perplexity on a held out 50 million token fine web ID set. The comparison is against vanilla loop transformers and depth-matched, non-looped transformer baselines. The headline result is that Hyperloop beats both of those categories while using roughly half as many parameters as the depth-matched transformers. Next, look at how performance changes when the number of loops changes.
What comparison should I focus on in this chart?
Focus on Hyperloop versus vanilla looped models at the same parameter scale. The authors vary loops from 2 to 6 for the 136 million and 579 million parameter settings. More loops help at first and then show diminishing returns. But Hyperloop stays better than the vanilla loop transformer across the loop counts they test.
Does the paper only claim a better curve, or does it say anything about smaller models beating larger ones?
It says more than a better curve. In a restructuring experiment, the authors make the middle loop smaller, but loop it more while keeping effective depth. They report that a 477 million parameter Hyperloop model still outperforms a full 1 billion parameter transformer, which is the concrete parameter efficiency story.
What did they learn about where to place the hyperconnections?
They ablate the number of hyperconnections in the looped block. The best setup is not the most heavily connected one. Applying hyperconnections after every loop works better than applying them after every layer. Even though the every layer setup uses more computing parameters, placement matters, not just adding more mixing. The paper also uses representation analysis to ask what happens inside the model.
What does this residual stream analysis add beyond perplexity?
Perplexity says whether the final model predicts better. This analysis asks whether the internal residual streams become redundant or stay distinct. Because Hyperloop uses multiple residual streams, the pairwise Cossini similarity view helps check whether those streams are carrying different information across effective layers and model scales. One more analysis maps intermediate residual states through the language modeling head.
What is the point of mapping intermediate states to vocabulary predictions?
It shows how prediction quality develops across effective depth, the row stack cost entropy, distribution entropy, and greedy decoding accuracy after projecting intermediate states with the language model head. That gives a second view of the same story. Hyperloop is not only smaller, its repeated blocks still build useful predictive representations through the loop.
What is the final takeaway?
The paper's takeaway is that looped transformers become much more competitive when loop boundaries get hyperconnections. The proposed architecture keeps the memory advantage of reusing layers, adds only a small amount of extra parameter and compute cost, beats looped and depth-matched baselines in the reported perplexity test, and keeps the advantage after post-training weight quantization.
So the important claim is not just fewer parameters, but fewer parameters while keeping the model competitive.
Exactly.